Hello everyone, this is the first in a series of lectures covering Chapter 40, Introduction to Quantum Physics. Before we begin, I'm going to read out loud the little storyline provided by the survey textbook about this chapter. It's time to putter around in your garage again and try to get your mind off the constant physics questions that arise from your daily observations. You decide to clean up a box of old equipment in a corner and throw away things for which you can see no need. While going through the equipment, you come upon something you didn't realize was there, an old variable transformer. You can plug an electrical device into its output and then dial in whatever alternating current voltage you want to apply to it, anywhere between 0 and 120 volts. You grab an old lamp, plug it into the transformer, and screw an incandescent light bulb into the lamp. You see a transformer at its highest voltage and turn it on. The lamp lights. Now you slowly turn the transformer voltage down. The bulb stays lit, almost all the way down to 0 volts. As the voltage drops, the light from the filament gets dimmer, but it also changes color. At high voltages, the light is yellow-white, but it becomes more orange as the voltage drops, as in the photo above. Why does that happen? You abandon your cleanup job in the garage and go into the house to read Chapter 40. In Chapter 38, we discuss that Newtonian mechanics must be replaced by Einstein's special theory of relativity when dealing with particle speeds comparable to the speed of light. For many problems, however, neither relativity nor classical physics could provide agreement between theory and experiment. As physicists sought new ways to solve these puzzles, another revolution took place in physics between 1900s and 1930, a new theory called quantum mechanics. This theory was highly successful in explaining the behavior of particles in microscopic size. Like the special theory of relativity, the quantum theory requires a modification of our ideas concerning the physical world. Because an extensive study of quantum theory is beyond the scope of this book, this chapter is simply an introduction to its underlying principles, but we will use these principles in our investigations through the rest of this book. With that said, let's dive in. Much like the textbook says in the storyline, classical physics cannot explain all the observed behaviors of light. It also can't explain most of the phenomena that has led the way in nuclear physics and electromagnetic radiation. So the well-established wave theory of light model in the 1800s wasn't enough to comply with what people were beginning to see and observe in that era. So into the 1900s, people like Planck and Einstein were developing theories to explain phenomena that classical physics couldn't solve. So they developed the working model of quantum mechanics to find a model for light and particles that could explain all the things that classical physics could not. You may have learned about thermal radiation in previous physics courses. Basically, anything with a pulse, anything with a temperature emits some heat. Just a way of saying we give off some radiation. Radiation sounds like a harmful word since, it's what turned Bruce Banner into the Hulk, or it's what, in realistic terms, radiation sounds like something that could harm your body. But remember that radiation, generally speaking, refers to any form of waves of the electromagnetic spectrum. So microwaves, radio waves, those are radiation. So is light from a light bulb. For our own bodies, right? We technically, at room temperature, we mostly give off infrared radiation, right? Not something you can see with the eye. And objects, though, that are hotter than room temperature will give off stronger radiation than that. By stronger, I mean more energetic, so higher in frequency. And that means that as objects get hotter, the radiation that they give off shifts towards the visible range from the infrared. So our bodies, not really going to produce enough. They're not going to reach a temperature where our bodies start to glow. But if you look at like the oxyacetylene torch here, or the oven at the bottom right, or stars even, you know that as these objects or the flame get hotter and hotter, they start to emit a colorful glow, eventually shifting from like a red glow to a bluer glow or even a white glow, since basically all visible colors of light are now the dominant radiation coming off the object. So in the quick quiz here, we're comparing two stars, Betelgeuse and Rigel, and the question is which one has a higher surface temperature? So the colder that the star looks, colder in quotation marks, by which I mean the bluer it seems, the whiter it seems in its color of light, because blue light is more higher. It's a higher frequency radiation than red light. It's the same as saying that red light is longer wavelength radiation than blue light. So since we said that thermal radiation tends to shift to higher frequency parts of the spectrum as objects get hotter, that means that an object gets hotter, starts glowing red, and then it sort of starts to go through the rainbow of the visible spectrum as it gets hotter and hotter. So it goes from red to green to blue. Then that means that Rigel then is hotter than Betelgeuse as it's glowing blue, which means that its ambient radiation is in the is closer to the shorter end of the electromagnetic spectrum. Now, there's a very idealized object that emits thermal radiation called the blackbody. What the blackbody does is it absorbs all incident radiation and eventually emits back its own thermal radiation, which for the blackbody gets called blackbody radiation. The explanation in classical physics as to why this happens is a little bit obtuse, and it is not necessary for you to fully comprehend its mechanisms, but nonetheless, they are explained in this lecture in detail. But basically, the blackbody lets you set up an idealized model to describe the notion of thermal radiation and nothing else. So it's a way to consider an object that the only thing it can really do is emit its own radiation. So nothing reflects off it, hence the name blackbody. Everything, all the incident radiation gets absorbed first. So just generally speaking, classical physics will explain thermal radiation of any object, even like of the infrared radiation that we emit at room temperature. Classical physicists would have explained that due to the nature of charged particles, and basically at any given body temperature or any temperature of any object, there's charged particles at the surface like electrons, and they're moving around. They have some distribution of energies, and the overall peak in the distribution, of course, shifts as the object gets hotter. But still, since all these charged particles have this energy distribution, over time, they just emit radiation, and that's what gets measured. Because the distribution of energies of the particles, of the charged particles, is continuous, then the radiation they emit is also continuous. Now, for a black body, as the one shown in the figure here, you can imagine then that light is entering the cavity of the black body. It is being absorbed. And what's basically happening is that the charged particles in the black body are absorbing the incident radiation, are then re-emitting it as thermal radiation. As the black body temperature increases, the electrons are more excited, and so they're more energetic, and so is the radiation they emit will also be more energetic. Nonetheless, at whatever temperature that may happen, the re-emitted radiation gets to stay inside the black body for a while. So standing wave patterns are produced, and thus the radiation that's being emitted takes on various frequencies and various wavelengths for all the possible modes of standing waves that can happen within the cavity. Now remember, though, that the energy of all these standing waves, at least in the classical model, doesn't depend on what the particular frequency your standing wave is, but rather it depends on the amplitude of the standing waves. And so more energetic electrons, which happen when the black body has a larger temperature, gets hotter, produce more energetic standing waves covering a bigger range of frequencies and wavelengths. So the radiation that's producing all these standing waves does eventually leave the black body, and that is the thermal radiation that is measured that can be detected. So the amount of energy, or more specifically the intensity, actually does depend on the temperature and also the wavelength distribution of standing waves. Now, the actual way to study a black body, since a black body is ideal, there's no such thing as a perfect absorber and a perfect emitter, like defined in the definition of black body. But despite not being able to make a true black body, what scientists were doing in the late 1800s is by basically creating a small metal box made of material like platinum and coating it with oxides like carbon to basically make it, as non-reflective as possible. They could create a approximation of a black body, basically kind of like a box where the inside acts as a cavity that they could shoot light into, have it absorbed, and let it, and would be then re-emitted as thermal energy coming back out of the box. Interestingly enough, you can do this experiment at home using a light bulb, which, despite not being a true black body, does emit thermal energy, and you can, much like they did with the more true to life black body, the metal box, you can then detect the thermal radiation that's coming off the light bulb and derive a black body spectrum. So a black body spectrum is just showing you the range of intensities that's coming off the black body in the experiment as a function of the wavelengths of light. So you can use a spectrometer to split the emitted thermal radiation into its various wavelengths to then measure which wavelength is most intense. And what physicists were finding was that the intensity, would peak at different wavelengths depending on the temperature. As the black body was heated to higher temperatures, the peak intensity shifted to lower wavelengths. And that explains why then, as things get hotter, they start glowing red and then eventually start glowing white as the peak intensity kind of covers the range of visible light. So you can then actually describe a relationship between the emitted thermal radiation and the temperature of the black body or the object. So despite the fact that, again, there's no true black body, so the these two formulas were to show are constructed with assumption of a true black body, so perfect absorber, perfect emitter, and thus they can still be applied to real world objects. It's just that they're not fully accurate. They're like idealized versions of what their output would be if they were a black body, but still it is a working model, much like ideal gases are in chemistry. So then when we do problems with blackbody radiation, we'll assume that we can use these formulas with the understanding that yes, it's not that the object is like an actual real black body that doesn't exist, but it is enough like a black body that we can use these formulas to describe their thermal output. So first we have Stefan's law, which basically relates the energy output, more specifically the total power emitted, so that's the intensity over surface area of the black body, as essentially being a function of its surface area, a Stefan Boltzmann constant, sigma, and the temperature of the black body to the power of 4. Now, as for the peak intensity, the peak wavelength, as we discussed, seems to become shorter. So it shifts to shorter wavelengths, therefore to higher frequencies as the temperature increases. This is described by Wien's displacement law that basically states that the product of the peak intensity wavelength and the temperature must be constant. So that means that as T increases, the peak wavelength decreases. So it becomes shorter. So in the classical model, though, this observation, so they were able to actually, the graph we see here was what physicists observed when measuring the radiation of a black body at different temperatures. Classical theories, though, cannot explain why there was a peak in intensity in the middle of the spectrum, because all wavelengths and frequencies of radiation are valid under the classical model, which means that they can all be produced inside the black body. They should all be emitted. And if they're all being emitted, then the more intense radiation will be the high frequency radiation, since with a higher frequency, that means that they're being emitted at a faster rate, so they should have a higher intensity. But clearly this is not the case. As we see, for even like 4,000 kelvins or 3,000 kelvins, really high temperatures, the dominant radiation of a black body is around the infrared range, or kind of nearing the visible range. This cannot be explained with classical theories. Understanding, light as a classical wave does not explain why there's a peak like this one. As a matter of fact, physicists tried to explain why the intensity was the way it was. But again, classical physics cannot provide an answer. Consider the Rayleigh-Jeans law, which was an attempt to describe the intensity curve. So with this formulation, the intensity is a function of both the temperature of the black body and the wavelengths of radiation being emitted. And this formulation, this description, does match the experimental results for long wavelengths. So for wavelengths in the range of like infrared or microwaves, this theory does properly predict what the intensity of those waves should be. However, the Rayleigh-Jeans law also predicts that the intensity of a black body for emitted radiation increases as the wavelength of that radiation gets shorter. So that means then that short wavelengths, so high frequency wavelengths, should dominate the black body spectrum. Then if we take this to its natural conclusion, then as the wavelength becomes shorter and shorter, the frequency becomes higher and higher, so the intensity would eventually become infinite for the waves in the black body that have very, very, very high frequencies and effectively zero wavelength. But then that would mean that experimental data would show this like huge curve where like the lowest frequency wavelengths dominate that the highest frequency, so lowest, shortest wavelength, highest frequency radiation dominate in intensity. But here we see on the graph that two lines. We see in red the observation done by the people conducting the Blackbody experiments, and in black we see the intensity curve predicted by the Rayleigh-Jeans law. So clearly, this intensity line would just go on getting higher and higher and higher, but in reality, there's a peak, not at the shortest wavelengths and not at the longest wavelengths either, but there's sort of a peak in the middle, which again the law does not predict. The law is predicting that intensity goes off to infinity as the frequency of light increases. This was a huge failure of classical physics, so much in fact that it was called the ultraviolet catastrophe. Let's go forwards in time to the year 1900, when German physicist Max Planck was able to develop a theory and a functional form for the intensity of a black body that could match the observational results. To do this, he had to change the assumptions about light. We had to stop considering light as this classical wave whose energy was independent of its frequency, and we had to start thinking of it as something else entirely. Let's begin then with Planck assuming that the thermal radiation in the black body is not produced by this chain effect of incident radiation exciting charged particles, which then produce standing waves in the cavity, which then gets out. Instead, consider the atoms in the black body having certain oscillations. So the black body, like anything else, is made of particles, made of atoms, and they all have some vibration. They all have some frequency to that vibration. And following that, he made two huge assumptions about these oscillators. Number one, so the atomic oscillators in the black body, have vibrations with some frequency f. The energy of those oscillators can only be a multiple of their frequency times a constant, which now we call it Planck's constant. So basically any particle has some frequency to it, and the energy of the particle is actually some multiple of the frequency times a constant. This means that since particles make up everything, and those particles have this energy that's a multiple of their, some component of their frequency, then that means that everything is fundamentally quantized. All oscillators, all these atoms, all these particles then occupy some quantum state. And again, the energy is a multiple of what we could now call Planck's constant and the frequency of their oscillations. And we're no longer in the optics chapter, so n used to be the index of refraction. N refers to the quantum number. It represents what energy level a oscillator is in. So an oscillator, with some frequency f, we're not specifying. If it's in quantum state of quantum number 3, that means that its energy is 3 times Planck's constant times its frequency. So then that means that this assumption that Planck is making leads to the conclusion that any system of oscillators of atomic particles can only have energies that are discretely separated. There's no continuous energy spectrum for particles. Following that, oscillators can jump between their energy levels. To do so, they must, by conservation of energy, either emit or absorb radiation. And if an oscillator then has to move to a lower energy state, then it jumps to a place of lower energy, which means it's releasing the surplus energy as radiation. If the oscillator goes up a state, it needs energy to get there, so it must be absorbing radiation. Then, if the oscillator absorbs radiation, it must do so with it must absorb just enough energy of radiation to get it to the level it needs to go. On the other hand, when the oscillator jumps down to a lower state, it releases radiation. It releases this like quantized packet of radiation that actually has the same frequency as the oscillator. And in the simplest case, then consider then an oscillator that jumps from its fourth quantum level to the third one. So it's just one rank down on the ladder. So the oscillator is here and it jumps over here. Well, it can do so. It just needs to release the amount of energy that separates the two states. So in this case, the gap in energy between level 4 and level 3 is just h times f, the Planck constant of the frequency. So then it'll jump down to this level and release energy in the form of electromagnetic radiation. And in doing so, produces, again, this like package of electromagnetic radiation. Classical mechanics, again, expected a continuous energy, but no, that's not the case. Whatever energy is being emitted is always some multiple of the frequency of the oscillator. Now, the Rayleigh-Jeans model working off classical physics assumes that the average energy of standing waves really just depends on the temperature of the body. It doesn't matter what the wavelength is, which again leads to the problem that if the average energy is the same for all wavelengths, then those of shorter wavelengths will have high frequencies, leading to impossibly high intensities which have not been observed. Planck's model, though, says that the average energy being produced from the radiation is the average energy difference between the levels of the oscillator, but weighed according to the probability of the wave being emitted. So different oscillators in different energy levels are more or less likely to jump to a lower level and emit energy. Oscillators that are in low frequency are then more likely to go down a step of the ladder than ones that have high frequency oscillations. And because of that, that means that low frequency oscillators, or long wavelength oscillators, are more likely to produce radiation, to emit radiation at a faster rate than the oscillators with higher frequency. This means that depending on the temperature of the black body of the object, you are more likely to see the lower frequency waves being produced at a faster rate than high frequency waves, which leads to an intensity that's dominated by lower frequency waves. So using thermodynamics, basically, Planck figured that for an atom occupying some energy state E, which depends, again, it just depends actually a function of its the frequency of its vibrations, of its oscillations. There's a probability of it being in that state relative to every other quantum state it can take on. And if you graph this, then you get an intensity curve that's centered around where the value of the Boltzmann's constant and the temperature is. So that's where the intensity peaks for those wavelengths that are around the value of kVt. So what I was saying earlier in the last slide, that basically if you look at the oscillators in the black body that have high frequency oscillations, their energy is pretty big. So the gap between energy levels is also really big, which means that there's a low probability that a high frequency oscillator in the second state or third state or whatever will want to jump down to a lower state. So they don't emit energy as often, which is why the intensity drops off for low wavelengths. However, for long wavelength oscillators, though, which are low frequency, the gaps between the levels are a lot smaller. The rungs in the ladder are a lot closer together. So they're more likely to want to jump down a step or two steps or more, and thus they're more likely to emit radiation. And because the radiation they emit has the same frequency and wavelengths as they do, this radiation gets emitted with long wavelengths. So there's a sweet spot where most of the radiation is likely to get emitted. And this model then actually does follow the experimental data very closely. And he was able to develop his own take on the intensity of the black body as a function of the wavelengths and temperature, which actually matched the experimental data much, much better than Rayleigh-Jeans ever hoped. But it is worth pointing out that the Rayleigh-Jeans expression does work for long wavelengths. So if you take the Planck formula for intensity, then take the limit as lambda as a wavelength that's really big, this does reduce to the Rayleigh-Jeans formula for long wavelengths. Interestingly enough, though, Planck had to develop this whole math model of assuming that particles, have discrete energy levels. He wasn't convinced about that. He felt that he just got lucky with the math. By coincidence, saying that everything is discrete just gave him a formula that worked out. Now, he had help. He had help to push idea from skepticism to reality to eventually becoming the foundation of quantum mechanics. Planck was still unconvinced, even when he proposed this whole model of blackbody radiation, which has now been proven to be correct. He was still looking for a more Commonwealth explanation for something that conformed to the wave theory of light, because this was making a very, very broad stroke in the fundamental reality of particles. So perhaps there was something much more rational of an explanation. But in 1905, while studying the photoelectric effect, Einstein re-derived Planck's results and pushed the idea even further. So basically, electromagnetic fields, their oscillations are also quantized. Everything's basically quantized. The electromagnetic radiation that's being emitted and absorbed by everything and any time in the universe carries discrete amount of energy. And this will eventually be developed into the particle theory of light, which would then be married with the wave theory of light to produce the full picture of radiation. You can see here in the picture Max Planck and Albert Einstein. Max Planck giving Einstein the Max Planck Medal in Berlin in 1929. So at around this time, it was the Wild West for physics. This is when modern physics really began. Lots of famous physicists, lots of thinking minds together, particularly in Europe and the United States, coming up with many explanations to the world of physics, well, just the world in general, that classical mechanics up to that point never dreamed it could. Also, Max Planck and Albert Einstein were friends. They not only liked to hang out and talk about science, but they were both musicians. Here's a nice photo of them I found of them playing piano together. Albert Einstein also played the violin, but apparently, according to the testimony of his neighbors, he wasn't a good player. So maybe take the whole image of him graciously playing on a violin with a grain of salt. Oh yeah, so Thermometers, they're essentially thermal radiation detectors. And because of the Stefan's law that says that the power that's being emitted by a radiator of thermal energy is its temperature is proportional to its temperature to the power of 4. That means that when you have a fever isn't really doesn't cause a dramatic shift in your body temperature. Really, your body only gets 1 degree hotter. So that's only like a less than 1% change in your temperature. But as for the output of radiation you're giving out, the power of your thermal radiation, because it's proportional to the temperature to power of 4, the amount of radiation that you give off increases by about 1%, kind of shown here. And this 1% difference in the radiation you give off when you're sick, is enough for any good thermometer to detect. As you can see here, this kid's trying to look as comfortable as possible while has to deal with the ear thermometer. Never had to use one of those, but it looks uncomfortable. Anyhow, a few examples here from the textbook. So this question kind of shows again, find the peak wavelength of the blackbody radiation, in this case, produced by the human body. So obviously it's not a black body, but the blackbody radiation is still kind of like a decent approximation. And the thing I want to point out is that whenever we use temperature, we have to use that in Kelvin. So whatever you have in Celsius, add that temperature, add 273 to that temperature in Celsius to get a temperature in kelvins. So in this case, you're now looking for the peak wavelength of a hot light bulb, and you can see that its peak wavelength is much shorter than that of the human body. We don't glow, but a light bulb does. And then the sun is much, much, much shorter. This question I really like because it's going back to the simple harmonic motion examples from earlier on. And basically, you just have a spring block system that's oscillating, and you have to define its energy. And you go ahead and you do that. You get the energy 2 joules. You can get the frequency of oscillations. But in the next part, you assume that it's a quantum oscillator. So you ask, well, with that frequency, what energy level is it at? What quantum state is it at? And 2 joules is actually a lot of energy. And then you find out that that's then the corresponding quantum number. Since the energy it has of 2 joules, in the model of quantum mechanics, this energy is some integer multiple of Planck constant times its frequency, but the frequency is pretty small, so it's Planck's constant. So it must be at a pretty big quantum state, at a pretty large quantum state, to be at an energy of 2 joules. In fact, the quantum state has a quantum number that is a lot of zeros. It's like a million, 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 million. Now, let's suppose that the oscillator jumps from the state it's on to the nearby lower state. So the closest state below it. How much energy is released? So if you're just jumping down one rung in the ladder, the energy release again is h times f. So it's a tiny, tiny, tiny amount of energy. So in the real world, right, objects carry, don't carry energy in electron volts like particles do. They carry energy in joules. So even though objects are made up of particles undergoing, random quantum transitions, those transitions create a very insignificant change in the energy of a real world object. So the effects of quantum jumps are not noticeable in the real world, despite the fact that energy is fundamentally discrete. The rungs, the jumps between rungs in energy are so tiny that in the real world, our perception of energy is continuous. Anyways, thank you for watching. I know that quantum mechanics can be a bit of a mouthful, so please take your time to digest and understand the material, and we'll see you next time.